Welcome, everyone. Hello, and thank you for coming to this session on high-performance predictive analytics in R and Hadoop. My name is Mario Inciosa, and I'm the U.S. Chief Scientist with Revolution Analytics. So for those of you who may not be entirely familiar with Hadoop, I mean with R. Certainly everyone is familiar with Hadoop here, but we're talking about R and Hadoop. And R has become the most widely used data analysis software. It's an open source project that's used by over 2 million data scientists, statisticians, and analysts. It's actually the most powerful statistical programming language. It's very flexible, and it's very extensible through a package mechanism. It's so flexible that it's used to create beautiful visualizations for organizations like the New York Times. And the thriving open source community is really keeping it at the leading edge of analytics research. It's become quite common when a researcher comes up with a new and improved analytics algorithm for predictive analytics or machine learning or statistics that they will implement that first in R so that they can share it with the community and have repeatable research. Finally, R is serving a very important role in filling the talent gap we see in data scientists in the enterprise. New graduates prefer R because R is, in many cases, in most cases, the language they've used and learned in university. So the skills gap with legacy systems is addressed by solutions that leverage R. So R is a fantastic open source platform, as I have mentioned, and it has great community support and over 5,000 packages, and that number is exponentially growing. So it's greatly, rapidly growing. But it does have some limitations. For one limitation is that the main predictive analytics functions in R, the ones that are built into the core of R, are memory bound. They run in memory, which is very convenient, but it does mean that you can't analyze data that's larger than the memory of your computer. Secondly, these algorithms are single-threaded, which does limit their scalability and the speed that they can attain. Finally, it is a community project, and enterprises need commercial-grade support. So that's where Revolution Analytics comes in. We provide extensions to R in a product, single product, that allows you to work with big data. It allows you to scale out across many parallel nodes. We provide commercial quality support and professional services. And of course, you can combine the results from your calculations with our packages and use those calculations with all of those 5,000 open source packages that the community has created for R. So this is a summary of our product, Revolution R Enterprise. At the bottom of the stack, we see the open source R, which we have enhanced by linking with the Intel math kernel libraries for additional performance. Then moving up the stack, I'm going to be concentrating primarily on the 3 blocks in the middle of this diagram, the scalar, distributed R, and connect R components. The scalar component is a suite of high-performance predictive analytics. The distributed R is our framework that allows those analytics to be distributed across many different parallel computing platforms, including Platform LSF, Microsoft HPC Server, Microsoft Azure Burst, to name several. And we've announced in February that we are going to have distributed R and our whole entire package integrated deeply with Hortonworks HDP. And that will be coming later this year. So that's really going to be the focus of my talk. Now at the top of the stack, we have our Develop R IDE. So we have an integrated development environment that provides you with all the nice features of syntax checking and name completion, a very, very capable debugger, and a nice object explorer, as well as graphics. And we have the Deploy R component, which allows you to expose what you create in R via web services, a web services SDK. So that's at the top of the stack. So what are our objectives for our product with respect to Hadoop? Well, our main objective is really ease of use. It's to allow our customers to do predictive analytics as easily in Hadoop as they can using R on their laptops. Of course, we're going to make it scalable and high performance. That's our heritage. And our goal really is to provide the first enterprise class fully featured suite of predictive analytics running in Hadoop. So a little overview of what we currently provide for Hadoop, because we currently have Hadoop capabilities that are quite popular with our customers. So we have the R Hadoop packages, the R Hadoop project, which consists of 3 packages. In the R Hadoop project, you may have heard about yesterday. Hortonworks had a nice talk on it. It is 3 packages that are sponsored by Revolution Analytics and contributed back to the open source community. They're called RMR2, RHDFS, and RHbase. So the RHDFS and RHbase, as their name suggests, allows you to share information back and forth between HDFS and the in-memory representation in R. Now, RMR2, that stands for R MapReduce, and what that does is it allows you to write your mappers and reducers entirely in R, working exclusively with R objects. So if you're most comfortable in the R language, you're a data scientist or statistician, but you want to have the scale-out power of MapReduce, and you have a custom algorithm that you want to have running on your cluster, you can use the RMR package today. You can also make use of Hadoop through our Revoscale R package, which will be the main focus of the talk today. Currently, it allows you to rapidly read and process data from HDFS, but we're greatly expanding that capability to allow the Revoscale R package of algorithms to run fully in Hadoop. So currently, those algorithms run on laptops, workstations, and servers, and MPI-based clusters and cloud. And what we're adding is the integration with Hortonworks in Hadoop. So last slide on R Hadoop. If you are someone who has a custom algorithm and you understand the MapReduce framework, and your primary language is R, the RMR package is going to make it very easy for you to write your mappers and reducers in R. Now, what we want to do is make it even easier for people who don't necessarily have the MapReduce background or don't need to write their own custom algorithm. Perhaps they're going to be working with a predictive analytics algorithm such as logistic regression or general linear models. And that's very hard to write it from scratch in Hadoop for MapReduce. So that's where we're bringing Revoscale R into the picture, which is an R package. It's one of these extension packages for R that's part of our product that adds the following capabilities. It adds data import, cleansing, and transformation capabilities. It adds the descriptive and predictive analytics, and those are parallelized and distributed. And it adds visualization for big data. Importantly, it's very portable and broadly applicable because it will scale from small local data to huge distributed data, and it will scale from laptops to servers to all the way to the cloud. And it's portable in that you don't have to change your code to run it on these different platforms. You just simply point it to the platform and data source that you would like to use. So a few of the ways that this package enhances R, we'd like to distinguish between the high-performance computing, which is parallel or distributed computing, and the high-performance analytics, which is parallel or distributed computing plus big data. So we support both of those modes in Revoscale R. Additionally, we have a file format, an XDF, we call it XDF, which is a binary file format that's very efficient and allows you to rapidly store and extract data. It works across all of our platforms, and we're porting it to Hadoop, so it'll be a splittable data file format in Hadoop. Of course, you can use the results from our high-performance analytics and HPC functions in your R environment, along with those other 5,000 R packages. Here's a summary of the big data analytics, going kind of in order, in the processing order that you might use them in real life, where you might start with the R data step to import and or transform your data. You might create factor variables out of continuous variables or integer variables. Then you might move on to the descriptive statistics and statistical tests to explore your data. You may work with some sample data as a start locally on your laptop, for example. Then you'll start to build predictive models, and once you've done that, you'll be interested in doing big data visualization, and certainly machine learning comes into play, and then finally the high-performance computing capability, which is the simulation. So giving you a little more detail in each of those categories here, I won't exhaustively read this list of features, but point out a few interesting ones. In the transformation category, we have the ability to recode variables and sorting, merging, and splitting data files. In descriptive statistics, we of course have things like medians and quantiles, and very importantly, we have correlations, covariances, and cross products, which are important for doing things like principal components analysis. We have statistical tests like chi-squared for categorical variables, various sampling capabilities. And then we move on to our predictive models, where we have multiple linear regression, generalized linear models, and we have logistic regression, as well as classification and regression trees. And of course, we can do prediction and scoring for all these types of models, and we can compute the residuals, which are the errors in the models. In data visualization, we have a range of big data plots, such as ROC curves, which are very important for classification. And in machine learning, we have k-means clustering and decision trees for classification. And then in that simulation category, we have Monte Carlo simulation. We expose a variety of very high-quality parallelized random number generators that are provided by the Intel Math Kernel library. So a little more detail on the high-performance computing capabilities. We have a function in our Revoscale R package that allows you to execute essentially any R function in parallel on the nodes and cores of your computing platform. And all the results from that then are returned by default to the user's laptop, although you could put in calls in your R function to write that data to HDFS or to HBase, for example. These functions allow you extensive control over how they're executed on the platform, and they're ideal for running simulations. Now, the HPCA functions, which I'll spend more time talking about, they're really interesting for big data because they handle an arbitrarily large number of rows in a fixed amount of memory. Unlike base R, they're not memory bound. Furthermore, they scale linearly with the number of rows, they scale linearly with the number of nodes, and they scale well with the number of cores and the number of parameters. And they've been engineered for extremely high performance. Now I'm going to provide you with a series of charts and experiments which show a little bit more about our scaling performance and our scalability. So in this particular chart, we're showing on the horizontal axis the number of rows, going from 1 million rows to 1 billion rows of data. We're building a linear regression model on that data, and it's a model with 443 parameters. And as you can see from this chart, the time to generate that model is scaling linearly with the number of rows. We're not hitting any memory limits, and we're not seeing any faltering of that linear scalability. In the next chart, we have an interesting situation where we're looking at a logistic regression model that we're building over, again, 1 billion rows of data, 443 parameters, but now we're looking at the scalability not in terms of the data size, but in terms of the number of nodes. And here we see a very interesting effect where we're actually seeing superlinear speed up as we go to more nodes. As we go from 1 node to 5 nodes, we're actually seeing that 5 nodes run 9 times faster than one node, rather than just 5 times faster, which is quite impressive and surprising. And we believe that the scalability, the fact that we're seeing such impressive superlinear scalability here is because as we go to more nodes, we're making more effective use of the distributed memory of those nodes. logistic regression is an iterative algorithm which has to make multiple passes over the data. And when you have more nodes, you have more RAM. And therefore, the operating system is able to cache more of the data set in memory. And therefore, even with a relatively large data set, you see this superlinear speed up. Now, the next comparison is giving you a little insight into how much care we've taken to make our algorithms high performance. In this case, we're running fully in memory. So disk I/O is not, it's not the fact that one algorithm has an advantage because it's in memory and one is disk. Here we're comparing the built-in linear model function in R, which is called LM, which is always running in memory. It can't run off of disk-based data. And that, we're comparing that to our function within Revolution R. So I'll start with the blue line, which is the linear model running in community open source R. And we see that that line, as we, on the horizontal axis, are increasing the number of rows in the data, we see that that line is ending somewhat short of 500,000 rows of data. What happened there with the blue line is that well short of 500,000 rows, we ran out of RAM on the 8 gigabyte computer that this was being run on. So you see that the scalability in R definitely is limited by the memory. Now in Revolution R, using the same built-in LM function, but now running in the performance-enhanced Revolution R, which uses the Intel MKL libraries, you can see that there's a performance boost going from that blue line to the red line. That's somewhat faster running with the Intel MKL libraries, but that doesn't solve the problem of memory limitations. To really break beyond that memory barrier, we have the RxLinMod function, which is our linear modeling function that is part of the Revoscale R package. That's the line at the bottom of the graph there, which you can barely see having any slope at all, but it does have a slope. That line there is showing that, first of all, at small data sizes, our linear model is much faster than the built-in linear modeling function. And as data sizes grow, we continue to be much faster, and we don't hit a memory barrier, even with 5 million rows. And that's because we basically use the memory very carefully and efficiently. We don't create many, many multiple copies of the data. So even when we're not running out of core, when we're running in memory, we still see a great increase in performance. So it gives you a little insight into why our algorithms are so fast. It's partly our very efficient memory usage. Here's a similar comparison for now the generalized linear model, which is a much more complex model than basic linear models. And here again, we're comparing in-memory data running in the built-in GLM function in R versus our RxGLM function that we provide in Revolution Revoscale R. You can see that the blue curve, which is open source R, has a much steeper slope, and it does run out of steam and hit memory limits below 500,000 rows with the 2 factors and 1 continuous variable that are in this data set. Whereas the Revoscale R is scaling with very little problem and great speed out to 5 million rows and beyond. So this is a very interesting benchmark based on data that SAS published in HPC Wire. Here we're again comparing linear regression, but it's on a very large data set. It's 1 billion rows. And this is the SAS, what we're looking at here is the SAS HPA product, which is their distributed product. In this case, SAS ran what they said is, quote, just a few parameters. They didn't reveal the data set, but they said it was 1 billion rows and just a few parameters running in memory on 32 nodes. These are hefty nodes with a total of 384 cores and 1.5 terabytes of RAM. So really quite a bit of hardware. And they were able to do the computation in 80 seconds. Using the Revolution logistic regression, we ran we tried to run a similar data set where it had 1 billion rows, and we weren't sure what just a few parameters would be, so we said, well, let's say 7 parameters. That's certainly more than just a few. We ran it on a very modest cluster of 5 nodes with 4 cores each, so 20 cores and 80 gigabytes. Each node of that cluster costs about $1,000. So a very, very modest cluster. The memory started out on disk, which is where we read the data from, as opposed to the SAS benchmark where the data started out in memory. And we found that we were able to complete that model in 44 seconds. So we had excellent performance, actually beating the SAS benchmark. And we estimate that we have delivered that performance at approximately 2% of the cost of the SAS solution. So our final comparison is one that was performed by Allstate, where they were looking again at generalized linear models. In this case, their data set was 150 million observations with more variables, 70 degrees of freedom. So they published this. This was published in a blog post in end of the year 2012. And here in this comparison, SAS was running on a 16-core Sun server, so an SMP machine. And it took 5 hours to do this generalized linear model. Then Allstate looked into doing an RMR MapReduce solution where they decided to see about re-implementing general linearized models themselves using the RMR package. And as I mentioned, it's not a trivial undertaking to write one of these full-featured statistical algorithms from scratch. So when they managed to implement that algorithm and run it on a 10-node, 80-core Hadoop cluster, they found that the time to fit was 10 hours. So it wasn't quite as fast as SAS, but it was still in a certain number of hours, more than 10 hours. They also said, well, we know R should be able to scale if it just has enough memory, so let's try running this on a server with a very, very large amount of memory. So they ran it on a 250 gigabyte server. It ran, but even after 3 days, it didn't complete. So that just was not a practical solution. And then finally, they ran it in Revolution R Enterprise, again on that small cluster I mentioned, the 5-node cluster. This time it was a cluster running IBM's platform LSF MPI library, and that completed in 5.7 minutes, which is just a really remarkable figure showing that it's very competitive and extremely efficient. So you're probably wondering what makes scale R so fast. How can we do this? Well, there are really a lot of factors that go into it. Certainly, one of the main factors is careful architecting for performance. So we've always had performance in mind in our product. We review every line of code with an eye to performance, and we have extensive profiling and benchmarking that we do on a continuous basis to make sure our performance is excellent. More specifically, we use very efficient computational algorithms. We have seen that we have efficient memory management because we were able to handle much more data in memory than the basic R function. So we do that by minimizing any copying of the data and converting of the data. A lot of conversions can be done on the fly. And we've written our code in C++ with very heavy use of C++ templates. So the compiler does a lot of work at compile time, and we have a very efficient runtime. Additionally, one of our very important advantages is the XDF file format, which is this very efficient binary file format that I mentioned earlier. So some more specific factors relating to our speed are that our algorithms will pre-analyze models to detect and remove duplicates in our computation. And you'd think, well, why would there be duplicates in the computation? Well, often when you're dealing with real-world data, especially categorical data, there are collinearities between variables. And that's essentially a duplication of a variable. You only need one of those collinear variables. So we can remove those duplicates, thereby handling categorical variables very efficiently. So I'd like to go into a little more technical detail here and explain how we create these algorithms like general linear models and linear regression and logistic regression. So our technique is called PEMA, or parallel external memory algorithms. Now, everyone here has heard of MapReduce, and MapReduce also is a type of PEMA, I would call it, or a parallel external memory algorithm. It's certainly parallel, and it runs by reading data from disk, so it's out-of-core external memory. So our high-performance analytics algorithms are also built on the same principle. Although they're not, strictly speaking, MapReduce, but our PEMAs consist of, rather than a mapper and a reducer, they consist of 4 functions that we've defined that we write to. And those functions are an initialize function, a chunk processing function, which is very similar to a map function, a results updating function, which is analogous to a reduce function, and then finally a results finalization function. So those are the 4 functions that we have to write to implement a new predictive analytics algorithm for our engine. And as I mentioned, these algorithms process data at a chunk at a time, so it allows them to scale to very large data and to be parallelized. An important feature of these algorithms is that when we're writing one of these algorithms, we're not writing them to a particular platform or a particular data source. So we keep what we call the compute context, which is the computing platform, separate from the algorithm. That compute context could be Hadoop, it could be MPI, it could be an SMP server. And we also keep the data source separate from the algorithm and abstract that. So our algorithms can work with data sources from a whole variety of data sources without having to be rewritten. So if you want to have a picture in mind, this big box at the top of the screen is the analytics engine where our PEMA algorithms run. And depending on the platform you want the algorithm to run on, that analytics engine will make use of the appropriate form of interprocessor communication, which might be MPI, RPC, sockets, or files, and it will read and process the data from the data source that you specify, be that an HDFS data source or a high-speed Teradata connector, ODBC. We also read SAS and SPSS data files, CSV files, fixed files, and of course our binary format, the very efficient XDF file format. So, to give you a little idea of how we're porting our engine to Hadoop, the base implementation of our port will process each iteration of our iterative algorithms, such as logistic regression, by using a separate MapReduce job. So the mappers will produce so-called intermediate result objects that are then combined by the combiner and the reducer. And then a master process, after that job completes, will decide if another pass through the data is required. A very important feature that gives us speed in Hadoop is this use of the XDF binary format. So the data can originally reside in XDF, or you might have it originally residing in, say, a text format. But because we will convert it to XDF on the first pass, we will only have to read and parse the text file once. Any subsequent passes through the data for these iterative algorithms will be done using the very efficient XDF binary format. Some performance enhancements that we're working on have been inspired by some of the very successful research projects to scale machine learning to thousands of nodes. And we're looking at using a single map job that'll handle all iterations. So this would reduce the overhead you have in Hadoop of starting each individual Hadoop job. And to increase the scalability to larger numbers of nodes, we can use tree-structured communication and tree-structured reduction so that you don't have all the reduction done in one reducer and all the communication coming back to one main node for reduction. And then we can use alternative communication schemes such as sockets instead of files. So those are a few of the performance enhancements we are working on for Hadoop. So that's my prepared slides. Thank you very much for your attention, and I have about 10 minutes for questions, if there might be any questions. And if you would, please use the microphones when you have questions.
Hi, my name is Pramod. You talked about the performance of logistic regressions. Have you done any research on clustering, k-means, hierarchical?
Yeah, I unfortunately don't have any results on the performance there. I haven't. I don't have anything on that right now.
Okay.
Mm-hmm. Yeah.
Second question, you talked about connectivity to HDFS, Hadoop. Do you have plans to have connectivity to Hive as well?
Hive don't. We haven't announced any plans in that direction. So basically, I've been talking, about the capabilities we'll be having on Hortonworks later this year in Hadoop, and yeah, I think HDFS and HBase are the main targets for data sources.
Okay, thank you.
Thanks. However, I would mention that because of the independence of data sources, that is, has allowed us to consume many different data sources. Yes.
So one thing I wanted to double check on, it seems like you have your own proprietary versions of some of the R functions that I'm assuming are inherently MapReduced versus it looked like if you're going to use some of the basic R functions that you guys haven't created your own version of, there the programmer would actually have to think through the logic of MapReducing whatever is occurring in that R.
That's correct. I would only tweak that a little bit to say that our functions are inherently parallel. They're not inherently MapReduce per se, because they're written using this PEMA framework so that they run on MapReduce as well as other parallel platforms.
Okay.
Yeah.
And one other follow-up is I'm looking into trying to utilize R in a commercial application or potentially Revolution Analytics.
Yes.
But with R being a GPL2 license, what are the implications of that? How safe can I feel, or what circumstances can your product be used for a commercial application given R's licensing?
Right, yeah. Well, there's really no danger in using our product in a commercial application because it depends on exactly how you want to integrate with it. But we've written packages that extend the open source version of R, so one could write a package, and then we have this deploy R framework that allows you to communicate with it through web services, which is a way to integrate with it, which wouldn't get you into trouble with GPL.
Thanks.
Any other questions? If there aren't any other questions, I can use a few minutes remaining just to give you a quick glimpse of what the code looks like when you switch from running locally, running on a local workstation, and you want to point it at your Hadoop cluster. So basically, it's a very simple change in your code. This is what your code might look like when you're running it on a laptop. You'll specify a data source. In this case, we're looking at some airline data. We can specify that airline data to be coming from your local data source. And RxLogit is the Revoscale R function for logistic regression. So here we're doing a logistic regression where on the fly we're creating a factor variable, which is the question of whether arrival delay is greater than 15 minutes or not. And we're looking to see how well we can predict arrival delay being greater than 15 minutes by using variables like origin, year, month, day of the week, carrier, another factor variable created on the fly based on departure time. And we're telling the logit function that we want to use this data set, which is local. Now, this is great. It's very quick to run things on your laptop. You don't have to wait for any job submission, and you don't have security problems, but you do want to scale to your big data eventually. So to change this to work with your big data, it's a very small change. You'll add that first line, Rx set compute context, and that will make your the Revolution interpreter that you're using aware of the Hadoop compute context that you would like to run the computation on. Then you'll change your data source from your local data source to your Hadoop data source, and then you'll run the exact same line as before to do the logistic regression, only now it's going to run in parallel on your cluster. So that is our portability advantage that we provide. That really insulates you from the details of the platform you're running on and any changes that might occur in that platform over time. So, do we have any other questions? I see a question.
Sorry if I missed this in the talk, but when you're using Hadoop, is it actually using the Hadoop streaming? Is that how it is implemented in Hadoop?
Well, we use Hadoop streaming for some functions. For our HPC functions, which I talked about, where it's not actually the data that is driving the problem, but it's the compute. There we do use Hadoop streaming. For the high-performance analytics functions, we're actually not using Hadoop. We're actually having a Java function which is calling calling R and then calling into C++ code. So it's a combination. Sometimes it's streaming, sometimes it's not.
So in the latter case, can it actually read data from HDFS and do the processing in parallel?
Yes, yes. So in the latter case, when we're not using streaming, we're using the full normal MapReduce with all of its flexibility. There we are, getting the input splits from Hadoop, and we're reading those files in the very fast C++ code.
And how are you then running the C++ code using JNI or something like that?
Yes. Mm-hmm.
Quick question about machine learning tools. So you have a K-mean clustering and I think some tree.
Yes.
Any plans to have more variety of algorithms? And is there any kind of expectations that their performance will be as good as that you've shown?
Yes. So we do have plans to implement additional functions over time in our platform. Functions like random forests and other popular functions will definitely be forthcoming. We've also put in stepwise linear regression and stepwise logistic regression, which are often used in practice. So we do anticipate additional algorithms being added, and we will also architect them to give the performance that we're seeing, this very high performance.
And about high performance, besides just MapReduce jobs, any plans to run it on a Spark cluster or like in memory?
So, our portability platform really allows us to make use of advances as they become available in the market and in the deployed base. So as things like Spark or Yarn gain traction, we can make use of those and have our engine make use of those capabilities of the platform without having to rewrite our algorithms, which are the PEMA algorithms. One more?
Yeah, I'm just curious. If you've got a foreign package, can you run that along with these, or do you need to split these into two separate scripts?
A foreign package, did you say? Or
Yeah,
yeah, like a package from the one of the 5,000 open source packages. Absolutely, you can run those packages using this HPC capability I talked about, which will run them in parallel over the cluster. And you can even use functions from those packages to do transformations on the fly for your data as it's being read and fed into these functions. All right. Oh, so curious, how many people are users here in today's talk? See a show of hands? So I'm seeing good percentage. 40, 50% are raising their hands, so thank you. That's great to see. Excellent. If there aren't any other questions, I think we're drawing to the end of the session, and there's a break immediately following the session, and I'll stick around for any questions people might want to ask offline. Thank you very much.